Okay, so we'll get started with the final material that we will be discussing. So that's the final sort of technical material we will be discussing. We'll be discussing BJTs or bipolar junction transistors, and very similar to the MOSFET, they are also three-terminal device. So it's a three-terminal device in which we have one terminal controlling current flow in between two other terminals. So that's the basic. So the basic construction will be very similar to the MOSFET from an external perspective. So three terminals, and the three terminals we will have in this device will be called emitter E, and base B, and collector C. So the base will be the control input that will be controlling the current between the emitter and collector terminals. Yeah. So, unlike the MOSFET, this is a device that can be used either as an amplifier or a switch. So same thing, exactly same. Yeah. So you will find that this chapter will be a review for what you did, except that the equations will be a little different, but it's the very similar explanation of everything that's happening in the device. Yeah, from a sort of external characteristics perspective, not the device physics, of course. So this is a much older device. It's a device that was conceived in 1948. So it's a much older device. So really, it was the workhorse until 2009 when the MOSFET took over a lot of the applications, right? So there are still many applications where the BJT is very useful and very powerfully applied, I would say. Uh, like harsh environment and high frequency applications, just because of the construction of the device. Uh, so it is still available. And what people have also found is that these BJT based circuits are much more predictable. So there's a lot of less, at the end of the MOSFET chapter, we were discussing the gain of the MOSFET, right? GM. And we were saying how GM is very dependent on all these parameters, and we came up with three different forms for GM, where we were controlling GM by what, the W over L ratio, the overdrive voltage, and the DC operating point, right? So the BJT is a lot more stable. So the gain of the BJT is not as dependent on as many parameters as the MOSFET. So circuits based on BJTs would be more predictable. So people used to like that. I mean, people like that about the BJT circuits. Yeah. The other thing is people realize that there are big advantages of BJTs in certain applications, like harsh environments and high temperatures, and then we will find a severe limitation very soon with BJTs. Yeah, is that unlike MOSFETs, the MOSFETs we were able to control. Our control input was a voltage, which is really nice because fine, you put a voltage, you're not really consuming current, right? So there's no power loss. In a BJT device, we will see that the control input is a current. So, and for you to maintain the device in a certain way, meaning, let's say you want to have a certain output current, you will have to maintain that current through the base. So you keep pushing current. So it becomes a big drawback. Let's say if you would like to control a circuit, you continuously have to have current, versus I just put a voltage signal, I'm not drawing any current, so power is almost zero. But in the case of a BJT, current will be consumed all the time to be able to control the device. Yeah. So people have, especially in switching applications, combined the benefits of a MOSFET and the BJT in something in a technology called BiCMOS. So it's a technology that includes both BJT type devices as well as MOSFET type devices together. And the power guys created what is called IGBT. So they created a BJT device, but with a MOSFET gate. So instead of having a control input being current like that we will see with the BJT, they merged the MOSFET and the BJT together and created a device that looks like a BJT on the output, on the power side, but it looks like a MOSFET on the control side, so that we don't have to be applying current all the time. Yeah. So that's a summary of the device. Yeah. So the device structure looks like this. Very similar to a diode, yes, two diodes. It's called bipolar junction transistor. So bipolar junction refers to, the fact that the current in the device is transferred using both holes and electrons. In the MOSFET, it was what? Either holes or electrons, right? The channel was either a P channel or an N channel. Here we will find that we will be transferring the current through both holes and electrons. Very similar to the diode, right? In the diode, the diffusion process was, from the P side to the N side, from the N side to the P side. Right here, I have two diodes. I have one diode like with these together, and here I have one diode with these together. Right. So the device is and it's junction refers to, of course, the junction between the emitter region and the collector region. So this is, and there are two complementary devices like the NMOS and PMOS. We have the NPN transistor, or the NPN BJT, NPN BJT, and then the PNP BJT. And again, very similar to the PMOS and NMOS, the biasing conditions that are required to put this device in at the DC operating point are flipped. The voltages are flipped. Very similar logic behind what we're doing. And the objective is to operate this device as an amplifier. We will see that, in amplifier mode, like a MOSFET, we will be able to model this as a controlled current source. And this controlled current source will either be voltage controlled or current controlled. So the MOSFET was only voltage controlled, right? So here it will be we can model it as it's a current controlled current source, but we can also model it as a voltage controlled current source using some manipulation of the equations here. The terminals we said are here: the emitter, the base, and the collector. And these are similar metal contacts that we had before for the diodes that are placed on the three terminals. And this is called the emitter base junction, and this is called the collector base junction. And these NMP form what's similar to a diode, and these NMP form what is similar to another diode. Yeah. Okay. So when will this device be operating in, as a switch, and when will it be operating as an amplifier? In the MOSFET, the device was operating as an amplifier in a region called the saturation region. So we had saturation region in the MOSFET, and then we had cutoff, and we had triode region. Right. So these were the three regions of operation of the MOSFET. This device, you will get confused because here the saturation region is saturation region in the MOSFET, which was the amplifier operating region. Here it's called active region. So, and triode region there is called here saturation. I didn't call them, right? So it's and then of course cutoff is cutoff. So the terminology is a little confusing. So, but anyway, so we have these two junctions in the device, and these are going to be. It's important to look at this table. So this table. So we have these two junctions in the device. So depending on whether this junction is forward biased or reverse biased, I will be operating either one of three modes. Okay. So before we do anything, when is this junction, the emitter base junction, going to be forward biased? Remember, it's like a diode. How do I make this junction forward biased? The emitter base junction forward biased. Where? Positive voltage in the emitter. I want it forward. I want this PN junction forward biased. Positive at the collector. No, I don't care about this one yet. I'm just talking about this PN junction. The emitter. I want the emitter base junction to be forward biased. How do I do that? How do I? Okay, this is my diode, right? PN. How do I make this diode forward biased?
To make it more positive in the P side.
On the P side, right? So if I put a more positive voltage on the P side with respect to the N side, then this becomes a forward biased
What if you put more negative on the AC?
If you flip the supply, it becomes reverse biased. Yes, right? So this is here forward biased. Correct? I forward biased this junction this way. So this junction now is forward biased. Forward. And how do I make this reverse biased? This junction reverse biased. A negative on the P side and the positive on the collector side. Right? So this would be voltage of the base with respect to the emitter. And this would be the voltage of the collector with respect to the emitter. Right? So I made this junction forward biased, and I made this junction reverse biased this way. Right? So in this operating mode, the device is in the active region. And active region is where we want it to be for amplifier operation, right? Before for the MOSFET it was called saturation. Here, its amplifier operation is called active region. So when I am forward biasing this emitter-based junction with and reverse biasing this collector-based junction, I am in the active region. One thing to note, okay? This is reverse biased, correct? The collector-based junction. And we said that in that case I'm putting VCE positive, right? But what if I put VCE 0? So let me draw this diode outside just for... Right? This is VCE, correct? And it's reverse biased. If I put VCE 0, is the diode reverse biased or forward biased? Why? What do you need to do to make the diode conduct current? Remember your diodes chapter. What do you need to do? More, but how much more? It's starting from 0.5. You have to overcome the forward voltage, right? Or approximately 0.7, right? So you have to be able to overcome the voltage, that's the barrier voltage, right? So which means what? Which means I can make this 0. I can make VCE 0, and this junction will still be reversed. Can I make this VCE minus 0.1? Why not? I can.
If you make it into block.
No, but it's still in reverse. It's still in reverse. It's okay. When is it going to be in forward bias? That's easier to explain the other way. When is this junction in forward bias? I will forget about this now. I will add another. It's like I will add this power supply, the other opposite side, right? This, if I put the more positive towards the P side versus the N side, this is theoretically forward biased, right? But remember, the model of a diode is what? When the diode is forward biased, my model looks like this. I have a voltage opposing the flow of current, right, equal to my forward voltage. And this forward voltage is basically the barrier voltage that we were talking about before, right? And this barrier voltage, depends on a few parameters, including the amount of dopant material that you have, and the barrier voltage for the diode, the PN junction that we discussed, was about what? 0.7, right? If I had reduced the doping and we look back at the equation, I can reduce that a little bit to 0.4, 0.5, right? But there is a barrier voltage that I have to overcome to be able to put the device in forward mode, put this PN junction in forward mode. We're okay with that? So, which means that VCE can be negative. How much negative? As long as I'm not gonna forward bias this. We will design these devices such that the emitter-based junction will have a barrier voltage that is higher than the collector-based junction barrier voltage. So when the emitter-based junction is forward biased, I will use the 0.7 volts as V forward that we talked about before in the diodes chapter. And when the collector base junction is forward biased, I will use about 0.4 volts. Okay? It's just by design. By design, I will make the collector region smaller.
There is a chance that if you change the voltage in VCE, it can cause it to become open circuit.
Excuse me, what do you mean?
So if it's like forward bias on one side and reverse on the other, it could cause like voltage current not to pass.
Is this forward biased? Which one is forward biased? Which junction is forward biased?
Let's say VCE is forward and VCE is reverse.
This is reverse.
And VBE is forward.
Sure. Then we're operating in active mode.
Okay.
Okay.
Then if it was VBE is forward and VCE is forward, what's will happen?
It's not forward mode anymore. It's not active mode anymore. It's
Saturation.
saturation. Exactly.
Which is like blocking the.
Which will reduce the amount of current passing through from emitter to collector.
Okay.
We will see that in
And
the.
that could be useful.
That can be useful, of course. That will be useful for our application. We will see it will be useful. Yeah. Sure. So do we see this is very important. This 0.4 is a very important thing. So VCE can be positive, can be 0, can be negative. How much negative? There's a limit on how much negative it can go. There is a limit on how much negative it can go before it gets into saturation mode. It will be the difference between these two. It will get into saturation mode based on because remember VCE. Sorry, this is what VB. Sorry, this is VBE, not VCE. Why am I calling this VCE? This is VBE, right? This is the voltage between the VBC. Sorry, VBC. VCB. Sorry, CB. Right. This is B with respect to E. Right, B with respect to E, and this is C with respect to B. So VCB can be positive, 0, some negative, until it's gonna push the device into saturation, cause this junction to be forward biased as well, right?
There's a number for the cutoff and then saturation.
Exactly. So there's a number for that for this VCB and VBE that will induce or put the device in saturation mode. And this is VBE, right? And this is VCB. How about this voltage? This voltage between here and here. We'll call this what? V. No. Always the arrow is pointing to the first letter. VCE, right? So VBE plus VCB equals VCE, right? So if VCB is negative, we said it's going to start changing. So if it's positive, we agree this junction is reverse biased. This PN junction is reverse biased. If it's negative, there will be a value beyond which it will push the device into saturation mode. In saturation mode, so I'll replace this VCB with a negative value, right? This negative, so it will be VBE minus a number, right? This number we said is what? About 0.4, and this number the forward voltage for the first emitter base junction is about 0.7, right? It will be forward biased, and the forward voltage that's opposing the current flow is about 0.7. And here, if it's forward biased, the voltage that will oppose the current flow is about 0.4. So 0.7 minus 0.4 is about 0.3 volts. So 0.3, 0.2. So in the textbook, they typically say it's 0.2 volts. What is this? This is VCE. VCE to move into saturation, not cutoff. Not cutoff. Cutoff means both are reverse biased. If both junctions are reverse biased, nothing is happening.
So
Current will not flow.
0.7.
Not 0.7. Remember, we designed the emitter base junction to have a different barrier voltage than the collector-based junction,
Okay.
right? And if I forward bias the collector-based junction, I have my forward voltage model for the diode, right? The forward diode, if it's forward biased, I have VF. VF for the collector-based junction will be about 0.4, 0.4, 0.5. And then VF for the emitter-based junction, which is forward biased to operate in active mode, is about 0.7.
So,
And we said that VCE is the voltage of the collector with respect to the emitter. That voltage is equal to, according to Kirchhoff voltage law, this voltage plus this voltage, right? If this voltage is negative, right, it's gonna be, there will be a point beyond which I can, if I create it more negative, I will forward bias this. That voltage that will make it more negative will be about the 0.4, 0.5, creating this forward bias junction. And this one, this device, will be it's already forward biased at 0.7. So VCE, the difference between the collector and emitter voltage, will be the 0.7 minus 0.4 or 0.5, which is the 0.2 volts. So this will be called VCE saturation. This is the point beyond which, this is the value of the collector to emitter voltage, at which the borderline happens at this PN junction, meaning this PN junction goes from reverse to forward.
So it becomes negative 0.5.
It becomes negative 0.5. Yeah, VCB becomes negative 0.5.
so VGT is just two diodes, and
Exactly, it's just two diodes.
yeah, and so we remember the diode was a graphite.
Sure, it will become very important.
So,
This curve of the diode current,
yeah. So
which, but in this case, we're not called diode current. It will be maybe emitter current,
so it will be the
or
same.
be collector. Exactly,
the same.
same equations as diode. Same equations as diode, because it's the same. I mean, it's just here instead of calling it the emitter current, it will diode current. It will be emitter current, for example, and here it will be base to emitter voltage, right? And here it will be collector current and collector to base voltage. Same. It's exactly the same. There are two diodes here. Okay, so summarizing again, I have this device is composed of basically two diodes. For me to operate in the active region, which is similar to the saturation region, which is the amplifier mode of operation, I have to forward bias this junction or this diode, and I have to reverse bias this. How do I forward bias this? By putting a voltage here more positive than here, and this is VBE. How do I reverse bias this? I put a voltage on the N side that is higher than the P side, and this is called VCB. Now the voltage between the other two terminals is called VCE, right? When this is forward biased, any diode when it's forward biased, I have a model that tells me that I have a voltage opposing the current flow equal to VF in a typical diode, silicon diode, with similar ratios of similar size PN junctions, PN regions. This VF is about 0.7 volts. So this will have a forward voltage of 0.7 volts across it. This diode, this is reverse biased. It was constructed to have a lower barrier voltage. It's constructed, that is by construction. I've divided, the area here is lower, and we will find that the barrier voltage depend on the area of the collector-based junction here. So because of the area difference in area, the barrier voltage is different. What is the forward voltage for the collector-based junction? It's about 0.4 or 0.5 volts, right? 0.4 or 0.5 volts. So if this is forward biased, I see a 0.4 or 0.5 volts across it, right? I do not want it to be forward biased in active region, but I have a mode of operation that I can create. If my circuit makes this diode forward biased, then I've entered into a different mode. It's called saturation mode. In saturation mode, this device is forward biased. When does this happen? It happens when I have made this more positive, the terminal, the P side more positive than the N side for this device. How much more positive? I have to be more positive than the barrier voltage so the current can conduct, right? So this region between them, this is the borderline between active region and saturation region for the BJT device. Okay? So we're okay with this? And then, like the diode, we still have, if the junction is forward biased, how is current moving? How is current moving? Using what mechanism? Diffusion or drift?
For the diodes, it's diffusion.
Exactly. It's diffusion for a forward bias, and it's drift for the reverse bias. No, it's the drift for the reverse bias and forward and diffusion for the forward bias. So if I'm forward biasing this, then there's diffusion from the emitter to the base, and if I'm reverse biasing this, then there is drift due to the electric field that is caused by the external voltage source that I'm adding. Right? So this is how.
So reverse bias is diffusion, drift, and
Reverse
forward
bias.
bias is diffusion.
Exactly. So these are my three modes, depending on how I operate the junction, the two junctions that I have. So as we said, active mode is the amplifier operation mode. The amplifier is forward bias for the emitter base junction and reverse bias for the collector base junction. Right? Cutoff, reverse, reverse. Reverse means nothing, no current is going to flow. And then saturation will be forward, forward. In saturation mode, I'm operating as a switch. We will see that it will be the mode where we will operate as a switch. Right, so it's a bit confusing from before. Here, saturation is like triode from MOSFET. Okay. So how does this device operate? So we said that we will put this in forward bias mode. So if I put the emitter base junction in forward bias mode, I have what? I have electrons diffusing from my. No, there's no channel. There's no. This is diodes. It's exactly diodes. And here we said it's called bipolar. Yes, we have diffusion here. Sure, exactly. Yeah. I thought you were talking about the channel creation. Okay. So here I created a forward bias here. So if I create a forward bias, so then I allow. So here I have lots of N donors, and here I have P-type material. So I have acceptors. So what happens is here lots of holes, lots of free electrons that will diffuse to the base, right? And then how about the holes on the base side? They will diffuse to the other side, to the emitter side. So if that's happening, where is the direction of current flow? So the electrons here are moving this side, and the holes here are moving this side. So the polarity or the direction of the current is in the same direction as the holes, right? So the emitter current will be in this direction, right? But one thing we will note is that we create this device with actually a very small base width for a specific reason. So what happens if the base width is small? That means the amount of holes that I have in the base are small. Right? I've added acceptors, but I have a small amount of acceptors. I already have a small width there, right? So when the electrons move from the emitter side, diffuse to here, are they going to find holes to recombine? They will find some, but they don't have enough because the width of this is much smaller than the width of the emitter junction, emitter area, right? So what happens is, fine, they will pass through. Some of them will recombine. Some of them will recombine in this base region here, right? So some of the electrons will be lost, right? But what does the concentration look like? Since they are diffusing from the emitter side to the base side, obviously the highest concentration will be, at the junction, right? And then as they move along, they will find some electrons to recombine with, and then a lot more holes than electrons in the p-side material. Obviously, they become a minority in the p-side material. So if we look at the concentration of the electrons as they move forward, fine, they will be high here, and then lower here at the end of the base. We're okay with that? I'm talking about the electron concentration. So they keep diffusing, right? They will keep diffusing into the base, and of course the holes here will move from the base to the emitter side, also by diffusion, right? This junction is reverse biased. Here I don't have too many holes that the electrons can recombine with. If they recombine, what happens? Then I've neutralized the charge. I don't have current flowing anymore, right? That's why if I create a small base, they don't have too many to recombine with. So what they do is they keep moving, and then they see a reverse bias junction. Reverse bias junction meaning the voltage here is higher than the voltage here. It means the electric field is in this direction, correct? The electric field due to this collector-base junction is in this direction. What does it do to the electrons that have diffused from the emitter side to the base and don't find holes to recombine with? They will push them through to the collector. They will collect them at the collector, right? So now I've created electrons that are moving from here to the other side.
And vice versa?
What do you mean vice versa?
Like, electron.
No, this is a reverse bias junction.
Oh, okay.
Reverse bias, right? This is a reverse bias. So you have high barrier voltage. So there is some saturation. Yes, there is electrons that will move against the electric field. No, they will not move with the electric field, right? So electrons move against the electric field, right? So no, you're moving the electrons in this fashion. Okay? So if I've moved electrons, meaning I have current. If I've moved charge, it means I have current, right? I have a lot of current between my emitter and collector, right? A lot of charge is moving there. How about in the base? Do I have current or not?
Wouldn't it pass?
Hmm?
The current wouldn't it pass?
But some of the electrons, some electrons will come here, recombine with the holes, and then what happens? And some of the holes here will go there. Some of the holes here will go there. Why are they going there? It's because I've made this forward biased, right? I've made this junction forward biased. So since the holes moved there, fine, it means that they will be collected at here. They will pass through my circuit, and then they will be re-added here again, right, from my base current. So there is some base current in this device all the time, right? So remember, versus the MOSFET, the MOSFET was controlled by VGS. It was controlled by gate to source voltage, right? As soon as I put in gate to source voltage, I've charged my plates, meaning I've created my channel. As soon as I've created my channel, I've created enough overdrive voltage to create the channel width. But now, and then, and that's not drawing current anymore. When you've created the channel, that's it. You've created your channel. You have enough charge to create a certain channel thickness. You are not drawing more current. Capacitors, as soon as you charge them, they don't consume more current, right? You've consumed some current to charge the capacitor plate, but then you just have voltage across the capacitor. Here, it's not the case.
So IB?
Yes, IB is
It's caused
continuous.
by
IB will be continuous.
but it's caused by the forward current.
Yes, IB will be caused by the holes moving to this side, diffusing from the P side to from the base to the emitter. Okay? And by some of the electrons that move from the emitter to the base, because they will cause current. Electrons move this way, the current will be in the opposite direction. So it's going to be current that will be, there will be we would think of this like a Kirchhoff current law, like a node. Current will come in through the base, through here, and then current will come from the collector, and then it's going to be out of the emitter, right? So do we see how this device works? Diodes, just diodes. I mean, really, if you remember your diode stuff, this should be straightforward. Yeah. Okay. So here in the next. So here they talk about this different in the concentration. So this is the electron concentration in the base, right? We said that fine, electrons will diffuse, meaning there will be a higher concentration here, and then they will move through the base region. They come to the collector base junction, which is very wide compared to the emitter base junction, and it's very wide because I've reverse biased it, right? So and then they are pushed over by the electric field due to the reverse bias of the collector base junction. Yeah. So that's how this stuff works. Yeah. So do we all agree now that if I make my base region small enough, that most of the electrons will move from my emitter to the collector, right? Do we agree with that? If that's the case, how did they move originally from the emitter to the base? By diffusion. And diffusion was the same mechanism as the current, the way that the current was created in a diode, right? So the equation for the emitter current and the collector current will be very similar. And they will all be based on the equation for the diode, which was what? Which was, a saturation current, some value, e to the voltage across that diode, divided by Vt, right? So, and we will utilize this equation a lot. And that, the equation where, the difference in voltage versus the two operating conditions for current that we used a lot in the diodes, we will see a lot here as well, right? So this is basically an application of the diodes material. So because the current will be due to this diffusion, and because the current is going to be basically proportional to the concentration of the holes and electrons that move, mainly now electrons, right? Because we made the base width very small. So the concentration will look like this exponential function, which like the diode case. And hence the current will also look like it will look like the diode current as well, but you will see that the equation for current will also contain this exponential as well. So if I would like to look at the amount of current that's flowing, this current is flowing through what? Through an area of the emitter, and it's mainly due to the electrons that have a certain amount of charge, and then these electrons have a certain diffusivity constant, and these electrons have a concentration that varies with the distance. Remember, because the current is what's gonna, it's the concentration that varies with the distance x. So this is the concentration difference that we're talking about.
So IN is the forward current?
IN will be the forward current, yes, or the diffusion current. So this is the electron diffusion current, which is basically the current of the forward current of the diode. Yeah. So we will find that this will be equal to the collector current, and to also be very close to the emitter current. So the emitter current and collector current will be very similar. Not exactly the same because of the whatever's happening in the base. Some of the recombination that's happening in the base and the reinjection of holes that's happening in the base makes a small difference between the current on the emitter side and the collector side. There's a small difference in current because of the electrons that are recombining here after diffusing it. Okay, but small difference. But all of these currents will be mainly due to diffusion, and they will all sort of follow the same equation of current as the diode. Okay? So let's move forward. Here, this minus sign just refers to the fact that current in electrons in the opposite direction as the flow of the electrons, as the concentration, basically. So now, the equations for current, right? So we said that, again, all of them will follow similar equation as the diodes, right? Because of the fact that they're all due to diffusion here, right? So, exactly the same equation. But the fact that of course you have to take into consideration the proper voltage. So why were they diffused? They diffused because I made VBE positive. Remember, I made my emitter-based junction forward biased. That was the reason why they diffused. So that makes sense that instead of the VD that we had before, we will have this as VBE, and this is the same thermal voltage that we had before. Right, and so here collector current is equal to the IN that the value that we just saw before, that depended on the area and the charge, etc., etc. So everybody's okay with this, and this is still called the saturation current. IS is still called the saturation current. Yeah. So and the saturation current will depend on what? Of course, a big dependence is on the width, inversely proportional to the width of the base. Right? That's why we want to make the base small. If you want to make the base small, then I'm able to push a lot of higher current, right? IS will be larger for smaller base, right? Okay. So any questions so far? So the base width is typically in nanometers. So just if you would like some dimensions, sort of, this is the base width. W is in the nanometer scale at the moment, and we said that IS, which is the saturation, is inversely proportional to W. This is the same as the diode current. IS is typically in the range of, since it's a diode, right? IS saturation current is in the range of what? 10 to the minus 15, exactly like the diode material we discussed before. So that's collector current. So everybody's okay with collector current? Okay. Collector current. Okay, so now the next component of current, and of course, one more thing is this is proportional to Ni squared. Ni is what? The concentration of electrons in intrinsic silicon, right? So this means that this is temperature dependent, right? So there's some temperature dependence as well. They talk about that here. So it doubles every 5 degrees C, for example. So that's one thing that they wanted to note here. So base current. What is base current due to again? Yeah, the fact since this is diffusing, since the electrons are diffusing to the p side and the holes are diffusing to the n side, basically we have a diode. This diode is between these two terminals, right? This diode is between this base terminal and the emitter terminal. Right, so since I have a diode, that means I have the same format for the equation. It will be a saturation current multiplied by e to the exponential of the voltage that produced it divided by Vt, right? But this value of the saturation current will differ in this case because the value of the saturation current depended on the area, the dimensions that we had in the circuit. And we said that, and it will depend on the amount of current, the amount of charge that is diffusing and staying between these p-n junction. But here we said that we made it small. Small meaning we also have a small amount of acceptors. So since I have a small amount of acceptors that are going to help diffuse the current, meaning the current diffusing from my base to the emitter is small as well, right? So because most of the electrons go through. Right? So since most of the electrons go through because they don't find holes to recombine with here, then the current at the base that's coming through the base is mainly due to this current injected through the holes. That's a biggest percentage of it. Some percentage of it is due to the electrons that are diffused from the emitter to the base and did not pass through, right? But the biggest percentage is this IB1 component. So there's the IB2 component, IB1 component. So the base current has two components, right? And since it's due to this small amount of holes that we have in the very narrow base versus the emitter, then this value is expected to be small, right? How much small? Is it a useful thing to make it as small as possible? Yes. So it's actually going to be a device parameter. So that will define the difference between the base current and your collector current. So it will be a device parameter called beta. It's a current gain. It will be called the common emitter current gain. We will see why it's called the common emitter current gain, but it's a current gain, right? So we will push. Remember, what are we? This device is a 3-terminal device that we are pushing or controlling the control terminal to control current between the two other terminals. The current between the other two terminals is what? Is IC or IE, right? We said IC or IE are the same, very similar, right? IC or IE are the same. This is my device, NPN. This is E. This is C. This is B. This is my control terminal here. I would like to. We saw that this is going to have to continue pushing current, right? Because I'm forward biasing this junction. If I'm forward biasing this junction, that means there's always current flowing here. There's always current flowing through here. What? IB is your control variable, your control input. We said that most of the electrons that actually go from here across by diffusion will actually continue going through, right? So, which means that if these electrons don't stay in the base, and since I made the base small, and I made the voltage here such that there's an electric field, as soon as these electrons pass through, they jump over to the collector side or collect on the collector side. Then what happens is the current between, the IE, the emitter current, and the collector current will be very similar. IE and IC will be very similar. We will see how similar they are, right? So
like IB represents.
IB represents your control signal.
No, but like you said, it's the difference.
What difference between? No, it will not be the difference. We will see that current will coming in from the collector IC, right? And then current coming in from the base, and then current coming out of the device through the emitter. So it's like having a node here, and this device looks like a node where IB plus IC is equal to IE, right? Thankfully, we made the base very small. Since we made the base very small, then I base is a small amount of current, but it exists all the time. Exists, right? The relationship between IC and IB is what? Is beta. And it's called the common emitter current gain. Right? I want beta to be as large as possible. Because if I make beta as large as possible, I can make IB very small, which means in this case that IC is equal to IE. That's what I would like to do. Correct? So beta is typically between 50 to about 200 in most BJT devices. Best case special devices, for example, can go for, they will have a beta of about 1,000. So what does this mean for, power applications? Let's say you want to push 1,000 amps through this device as a switch, right? So what does this mean? No, that means I have to keep pushing 1 amp continuously, right? If beta is 1,000, we said this is a special case actually. If I'm pushing 1,000 amps through, if IC is 1,000 amps, that means I beta is 1 amp all the time. Can you imagine 1 amp? 1 amp is continuously having to be pushed through the base for you to push 1,000 amps through this device.
Like it helps. Like
it's a control signal. It's because the device because the junction is forward biased. Since the junction is forward biased, it's a diode. The current will flow between the two terminals of the diode. How much current will flow? Go back to the PN junction. Current will flow in the PN junction due to diffusion. The diffusion of the electrons from this side to that side, holes from this side to that side. The electrons, as soon as they pass through, they see a very narrow base and they see a big electric field. They are pushed straight through. So really, it's mainly due to some of the electrons that are diffusing from the emitter to the base, and the holes that are diffusing from the base to the emitter side. So it's a small current. But it has to be there. It has to be there for the diffusion process to start. Right? So I don't like that, because versus the MOSFET I just needed to put a gate to source voltage. I did not have to consume current all the time, because current flowing is flowing through where? Through material that has some resistivity. Means power loss, right? So, okay, so as we said, this base current, which will have two components. One, due to the holes diffusing from the base to the emitter, and one due to the small amount of electrons that are moving from the emitter to the base. So they will both be flowing through my circuit. Most of the electrons will pass through, though. Since that's the case, then I base and IC, or the collector current and the base current, are related by a device parameter called beta. We're okay with that? Which means that the base current, the shape of the base current will look like what? Shape of IC is equal to what? So IC was equal to IS, e to the VBE over VT, which means IB, the base current is IS over B times e to the blah, blah, blah. Right? So same format. So the base current, the collector current looks like this. The base current looks like this. The emitter current will also look like this. This was also due to diffusion. But we will find, instead of alpha, instead of this beta, which is called common emitter current gain, we will have another variable called alpha that will relate the collector current and emitter current. And we expect alpha to be very, very close to 1. Right? Do we understand why it has to be close to 1? Yes? Okay, so now let's move on. So this is the format of the base current that we were talking about. Now the last current that we need to talk about is the emitter current. So we said that this device will look like a node, basically. We're injecting base current, collector current from one side, and then the output will be the emitter current. Right? So my collector current plus base current is equal to emitter current. We know that collector current is IS e to the exponential, the same exponential, right? Over, and then this one is IS over beta, same exponential, right? If I add them up, I will get an expression for IE in terms of IC and beta, right? If you simplify, you substitute with the value with IC that we have. IC was equal to IS, which is my saturation current, e to the VBE e to the VBE over VT, right? I will call this beta plus 1 over beta, I will call it alpha. The beta plus 1 over beta, yeah, beta plus 1 over, no. I will call the relationship, so this is what? This is IE and IC. I'll call this beta plus 1 over beta, I'll call it 1 over alpha, right? So I'm relating IC to IE with an alpha variable, right? So IE and IC are related by beta plus 1 over beta. I'll call this beta plus 1 over beta, I'll call it 1 over alpha. Okay, so just another term here, right? So it's a term that relates your collector current and emitter current. So if this is 1 over alpha, then if this is 1 over alpha, then IC is equal to alpha times IE, right?
So we have a relationship between IB and IC, and now we have
Yes.
IB and IC.
IB and IC are related by
Beta.
beta, and IC and IE are related by alpha,
The alpha is in terms of beta.
and alpha is in terms of beta. So, and it makes sense because they're all diodes. It's all diodes, and it's the same diode that has the saturation current to be the same, assuming the areas and the concentrations are the same. Since they are not the same, there's a variable that, a scaling factor that relates the different diode currents, basically. So I have, two different diode currents that are related by variable beta. Okay. So now that's the case. If that's the case, everybody's okay with this. So I can rewrite the emitter current instead of in terms of IS and alpha, which was IS is my saturation current, and this is 1 over alpha, right? So I can rewrite emitter current in this fashion. I can relate, I can write alpha in terms of beta or beta in terms of alpha. right? So all of that is possible. The one thing that we should note here is what? Is small change, alpha is what? Alpha is very close to 1. Because we said beta is large. So if beta is large, then beta over beta plus 1 is almost 1. Right? But, which means alpha is very close to 1. So here, beta was 1 was insignificant in relation to beta. But here, 1 is quite significant in relation to alpha. Right? So any small changes in alpha will mean big changes in beta. Right? So we will find that in practice, actually, beta is highly affected by the manufacturing process. So you will get a device that you will be given beta in a huge range. So beta will not be a nice fixed variable. Not beta equals 100 is an ideal thing to consider, right? Yeah, it's a number, but it's a range that's very big, yeah, because it's very highly affected by the manufacturing process. Okay. Now, before I move to the next page, so now what do I have? We have now I'm going to model, come up with a circuit model, the equivalent circuit model. What do you think this equivalent circuit model will look like? Remember, we have, remember I have a current here that is controlled by a voltage. Do I have anything else? Remember, BE voltage, VBE is my external voltage that I'm applying. So this external voltage that I'm applying is actually controlling my current. And we know that IC and I alpha are related anyway. So which means that my collector current is also controlled by this base to emitter voltage. So in all cases, actually, what I've created is a current source that is controlled by a voltage. Okay? So, which helps me introduce the model. So again, we said beta will be called the common base current gain. I'll show you why it's called the common base current gain. So these are the models for the various models for the device. So there are two different families of models. So okay. So what's happening here? Remember, we said that IC is equal to IE times alpha. And we said that IB is equal to IC divided by beta, right? Remember, this was my device. This was my emitter, base, collector. This is my control input, IB. This is IE, and this is IC, right? So IC and IE are very close. IC and IE are very close. And they are related by a variable alpha that is very close to 1. And then I beta is a much smaller variable related to IC by beta, which is a current gain, right? So now let's see how this if this equivalent circuit model helps explain what we're talking about or not. So I have my 3 terminals here. My currents, all 3 currents are here. And then what do I have? I have current flowing through from my base is I forward bias this diode, right? Remember, we have to forward bias this diode to operate in the active region. So I forward bias this diode using my VBE. If I forward bias this diode, then I have current flowing through, right? And this current flowing through will be, one component will due to the forward bias. The other component will be due to collector current flowing through here as well, right? So the emitter current will be composed of the base current and this collector current. This collector current, we said, is the same as the diode current, IS e to the VBE over VT. We're okay with this? So this was basically my diode current from before. This diode current, and now this base current is equal to IC over beta. Base current here is IC over beta. So it's, I know what this looks like, I know what this looks like, right? So this is IC over beta, which means it's IS over beta, basically. It has a peak value of IS over beta, right? This has a peak value of IS, this has a peak value of IS over beta, compared to the collector current, yeah. And then the emitter current, how is the emitter current related to collector current? By alpha. So if the collector current is IS e to the x, then this is the collector current. How about the emitter current? It's IS over alpha e to the x, right? So that's why they have this IS over alpha over here, right? We're okay with this? So does it make sense? We sort of, fine, we consider this very small, consider the base current very small, beta is large, alpha is close to 1. If that's the case, the collector current and the emitter current are related by this alpha. And that's how they're related. So what do I have here? I have a collector current that is controlled by voltage, right? So this is a voltage controlled current source, right? I have a current source between my collector and my emitter. I've created a current source between my collector and emitter that's controlled by my base to emitter voltage. Okay? So this configuration is called a common base configuration. Common base meaning the input is on the base and emitter, and the output is on the, so the base is a common terminal between the input and output. So if my input is here, my output is the collector current, so the base is sort of common between them. We'll find later that common base configuration means the base will be grounded. Common emitter configuration will mean the emitter will be grounded. But this is a circuit model that has input on one side, output on one side, and a base is sort of the common terminal between them. That's common between the collector and base, and common between the base and the emitter. So it's called a common base configuration. And this is, again, a voltage controlled current source. Voltage controlled current source. Because of this, I've created a voltage controlled current source, right? This is a voltage controlled current source, right? How about this one? What does this look like? So let's see, again, we have IC is equal alpha times IE, and IB is equal to IC over beta, right? So how does this look like? What does this look like? Does it satisfy our equations? Right, these are the equations that we have. So we have current flowing through my base, forward biasing the base to emitter junction, right? So I have VBE here, right? That looks like a diode, and that current we said is going to be added to collector currents, and they will both create the emitter current. And this collector current is the same as this, IS e to the VBE over VT. Same. Maybe this, you cannot see this if you zoom in. It's the same. This here, it's e to the IS e to the VBE over VT, right? So this and this, satisfy our equations, and they are both what? Both of these are current voltage controlled, because here e to the VB, and I've created the current source. This is e to the VB, and I've created the current source. That's controlled by my base to emitter voltage. Current source here controlled by my base to emitter voltage. So both of these are current controlled voltage source models of the device that satisfy our equations. How about here?
Sir,
Yes.
is it current controlled
No.
voltage source or voltage?
No. It's a voltage controlled current source. It's a current source. They're both. The output of the devices is a current source.
So it's like the most.
Exactly like the MOSFET. Exactly like the MOSFET. Just that the gain will be different. The gain is different. You remember in the MOSFET, in the active region, what was the drain current controlled by? The over voltage squared. In the MOSFET, in the saturation. Here, this is also active, this is relevant in the active region as well, because the idea of this being forward. This is forward only in the active region, and I've created the other one reverse. That's why all the equations apply to what we're talking about, active and reverse, right? Active in the electron emitter base and the reverse in the collector base junction here, right? So I've created current sources controlled by voltage. Current sources controlled by voltage. So my equations also tell me that I can, the relationship between the collector current, what's the relationship between the collector current and the emitter current is IC is equal to IE times alpha, right? So I can, rewrite this, redraw this. Instead of writing IS e to the VBE over VT, I can, this is IC. IC is equal to alpha times IE. Alpha times IE. So I can do that, right? And in this case, and this one is similar here. So I have forward biased, the base emitter junction, forward biased, the base emitter junction. This current is summing up into IE with IC. What is IC? IC is equal to beta times IB, right? My other equation is IB is equal to IC over beta. So I have IC here, which is equal to beta times IB flowing, adding up with my base current, adding up, going out to the emitter. And these are what? Current sources, yes, controlled by what? By current. So these two models are current controlled current sources. And these two are voltage controlled current sources.
In MOSFET, we couldn't switch between.
No, here you can switch. Here you, depending on what you're given in the problem, you will choose this model or this model or this model or this model. All of them are controlled by I-base, right? So sorry, this is voltage control. So it's voltage control current source. So this is controlled by VB. Here, which current is controlling? It's the emitter. Emitter current is controlling the current source. And the emitter current, I can control it by VBE. Remember? Because the emitter current is due to the diffusion. Yes, but I have to maintain current flowing. That's the difference, is current in the base will always be continuous. Right? So there, I did not have to have continuous current. Yeah.
So,
Yes.
do the same thing, no?
What?
I do also the same one.
Homework for the MOSFET? Yeah, here.